Okay, good afternoon, everybody. Thank you for attending today's colloquium titled Catching the Sources of Ultra-High Energy Cosmic Rays by Dr. Kumiko Kotera. She studied at the Pierre and Marie Curie University in Paris and did a postdoc at the University of Chicago and then at Caltech. She has been the recipient of several grants, fellowships, and awards throughout her career, such as the Young Star Early Career Recognition Award by the American Physical Society and a bronze medal at the CNRS, which is the National Center for Scientific Research in France. She is currently a permanent researcher at IAP, which is the Institute of Astrophysics of Paris, and co-spokesperson of the GRAND experiment, which we will actually hear about in the talk. As always, we ask the audience to keep your microphones turned off during the talk. Any questions can be written in the chat during the talk, or you can make them by raising your hand when we have some breaks. We welcome Dr. Kotera, and we can begin the colloquium.
Thank you. Thank you very much for your nice introduction and for the kind invitation. I'm very happy to be here tonight across the ocean. And yeah, I hope that I prepared my talk at the right level. Maybe it's going to be a little bit too low level. In that case, just let me know that if I should accelerate. But okay, so anyway, I'm going to talk today about the prospects of doing EeV astronomy in the next decade, and about catching the sources of ultra-high energy cosmic rays, which are themes that are very linked to each other. So we're living very exciting times. In 1962, the very first ultra-high energy cosmic rays were detected, but we had to wait for more than half a decade before the next very exciting, very high energy particles were discovered, and these were high energy neutrinos at PeV 10 to the 15 electron volts detected by IceCube. But then things escalated as 2 years later, the first gravitational waves were detected, and then gravitational wave astronomy began in 2017 with a joint detection of a kilonova with a binary neutron star merger. And the same year, the extragalactic origin of ultra-high energy cosmic rays was confirmed. And PeV neutrino astronomy began, maybe, with the coincident detection of an IceCube neutrino with a blazar flare. Meanwhile, in gamma rays, there were many new classes of sources that were detected, new tidal disruption events, magnetar flares, blazar flares, and also in other wavelengths, fast radio bursts, also gamma ray bursts, superluminous supernovae, and etc. So it seems like we are living a new era of multi-messenger astrophysics, with many messengers being detected and puzzles being solved, but we still don't know the origin of ultra-high energy cosmic rays that were detected more than 60 years ago. So let me talk a bit about these ultra-high energy cosmic rays and why we have a problem with them. So you know that cosmic rays are nuclei, atomic nuclei, like protons, or heavier nuclei like iron. And some of them reach the Earth with amazing energies of order 10 to the 20 electron volts. So this is the flux that we have, that we observe of these cosmic rays on the Earth. And you can see that it traces this very nice power law over many orders of magnitude in flux and many orders of magnitude in energy. And around mid energies, what we call mid energies, which is already very high energies, around 10 to the 15 or so electron volts, we know more and more that cosmic rays come from our galaxy and are accelerated in supernova remnants. But if below we have hints that we know also that cosmic rays are produced in the sun, and that they're produced in a galaxy above, etc. But above this energy, we don't know yet what sources are producing ultra-high energy cosmic rays. And this is a puzzle that we would really like to solve. Well, 10 to the 20 electron volts, it's a macroscopic energy. It's like 10 joules. It's the energy of a tennis ball hit by Roger Federer in a subatomic particle. And to get an idea, at the LHC, particles are accelerated 10 million times at 10 million times less energies. So it's, well, it's gigantic, but, and we think that such high energy particles would be produced in the most powerful sources of the universe. But the reason why we haven't yet identified those sources is probably because the universe is magnetized and because these cosmic rays are charged. So if you have a source that emits cosmic rays, because the universe is magnetized, it's going to be deflected by these magnetic fields. And when it arrives on Earth, and if we look at the arrival direction of this particle, we don't see the source, we lose track because of these deflections. And well, you know that our galaxy, clusters of galaxies, and our entire universe is magnetized. So we really completely lose track of these particles usually. And I said that probably the most powerful sources in the universe were producing these ultra-high energy cosmic rays, but the problem is that these most powerful sources are also the ones for which the workings, the evolution, the emission mechanisms are not well understood. So this is also an astrophysical reason why we don't understand the origin of ultra-high energy cosmic rays. And finally, another probably one of the major reasons also why we don't have an answer to this question of the origin of ultra-high energy cosmic rays yet is that at these ultra-high energies, the flux of these particles is extremely low. We have about 1 particle per kilometer square per century at 10 to the 20 electron volts. And with such low fluxes, we really need to build gigantic detectors in order to collect a large statistics of these events, of these particles. So we also have a statistical problem. And if I may, I'm going to tell you about the journey of ultra-high energy cosmic rays. And this is also going to give you a picture of why we understand so little about the origin of these particles. So when a particle is emitted by some source, they are injected in some way, which we don't understand. They're accelerated by some mechanism that we don't understand in an outflow of which we don't really know the structure, the magnetic field, the size. So there are many unknowns here too. And if the particle manages to escape from the source, to be accelerated and escape from the source, it's going to be deflected, as I said, by intergalactic magnetic fields. And the problem is that these magnetic fields are not well known. So this is another unknown. And also particles are also, interestingly, they will, while they propagate, they will interact with cosmic backgrounds, CMB, UV optical and infrared photons, and produce secondary neutrinos and gamma rays, which could also be observed on Earth. And this is very interesting because maybe these particles that are usually neutral will point back to the sources, and this could give us a very interesting way to probe the nature of this source. These secondary particles, neutrinos and gamma rays, can also be produced inside the source while particles are being accelerated or try to escape. And these other neutrinos and gamma rays could also be observed on Earth. We also don't have a good understanding of the source population and of their emissivity evolution. So in time, while the universe evolved. So, and this is going to affect the observables that we will have on Earth, and this is also not well known. So there are so many unknowns here, But we still have some observables that we can play with and from which we can try to understand what's going on. These observables are, for ultra-high energy cosmic rays, the mass, the spectrum, and the distribution in the sky of their arrival direction. So they're anisotropy in the sky. We can detect secondary neutrinos with different parameters, observables, multi-wavelength photons associated to these events, and maybe sometimes gravitational waves if the sources are very compact. So what we're going to do in the next minutes of my talk is to use the ultra-high energy cosmic ray observable and see if we can learn anything about the sources of ultra-high energy cosmic rays. And these observables, again, are the energy spectrum, the arrival direction in the sky, and the mass composition. So if we start with the energy spectrum, this is what we know about the cosmic ray flux. So it's the same flux as I showed before, but we multiplied by this E square here to try to zoom in and to see, and we see then that the power law, that the beautiful power law that we saw is not perfect, but it is bumpy, and you can see some breaks in the power law that we call here the knee, and here the ankle, and here also we see, so these could be associated to cosmic ray propagation features, or also features related to different sources of cosmic rays. And then what's very interesting is that at the very highest energies, we see that there is a cutoff. And this cutoff could be either what we call the GZK cutoff, which I will explain later, or the just a signature of maximum acceleration energy, just that the sources are running out of fuel. If it's not the maximum acceleration energy, it could also be, so this GZK cutoff. The GZK cutoff was predicted by Greisen, Zatsepin, and Kuzmin in 1966. And what they remarked is that, so ultra-high energy cosmic rays should interact with the CMB, the intergalactic photons, on their flight from the source to us. And while doing so, they're going to do pion photoproduction and pair photoproduction. But what's really important is this pion photoproduction, for which the interaction threshold for protons is of 6 × 10⁻⁹ electron volts, roughly. So it means that above this energy, you're going to have lots of interactions and particles are going to lose energy. So here you see the proton energy loss length as a function of energy. And you can see that if you take, so you can see that this is the photopion production. You can see that at the highest energies, you lose energy very quickly. I mean, if you propagate over short distances, you're already losing a lot of energy. And for example, at above 6 × 10⁻⁹ electron volts, you can only propagate to around, say, 300 megaparsecs at most. And this is very interesting. It means that, and this is responsible of this could be responsible of this GZK cutoff. So if sources are located at cosmological distances, particles should interact with these different backgrounds, and they would lose energy, hence the cutoff in the spectrum. But it also means that if we're looking for the sources of these ultra-high energy cosmic rays that we observe on Earth above 6 × 10⁻⁹ electron volts, we only have to search in our local universe, because there is this horizon here of a few hundreds of megaparsecs beyond which cosmic rays cannot travel. So the extragalactic sources of ultra-high energy cosmic rays should be located within 200 megaparsecs. So we learned quite a lot from the spectrum already, and we could actually dig more into the features and learn even more. But sorry. Let me now talk about another observable, which is the large scale anisotropy, anisotropies of these events. So how cosmic rays arrival directions are distributed in the sky. And this is going to tell us whether the origin of these ultra-high-energy cosmic rays is galactic or extragalactic. So let's assume we have a galactic source of ultra-high-energy cosmic rays. If this is the case, for example, if we have one source in our galaxy, then we should see a blob in the sky coming from one direction. Even if the particles are very charged and are super heavy, they should still cluster in one direction and create a dipole signature. Because the magnetic field of the Earth is quite strong, but still the deflections shouldn't be erasing completely the direction of this single source. So then people calculated that if we have a galactic source, then the level of the dipole amplitude should be of order, sorry, I'm trying to put out the, so the level of the dipole, for example, for proton above 8⁻18 electron volts is going to be of several tens of percent. And so this is one thing that we could try to measure in the sky. And if you take, another study showed that if you take extragalactic sources that are distributed further out, and you calculate the dipole amplitude again, you take all the arrival, you simulate some sources in the sky, you propagate cosmic rays, you calculate the dipole, the dipole signal and its amplitude, and then you find that at 8 EeV, 8⁻18 electron volts, so sorry, it's not the same scaling here and here. So here you have a level of less than 10%, around 5% at most. So you really have very different signatures in this dipole level. And what we saw with the Auger data, so Auger is an observatory of ultra-high-energy cosmic rays located in Argentina that you know of. So what we saw was that the level of dipole observed in the cosmic ray data is of 6.5% above 8 EeV. And this is a strong result at 5.2 sigma. So this means that we exclude completely above this energy the possibility that the sources of ultra-high-energy cosmic rays are from galactic origin. And this was quite a good, nice confirmation of what we thought was the case, but at least we know where we start with extragalactic sources. So this is what we learned from anisotropies in the sky, but now let's look at the composition. So the composition of ultra-high-energy cosmic rays is still quite complicated to interpret. Also because we don't have a very clear data yet. So what you can see here is the for an energy range from PeV to 10⁻20 electron volts, you can see how the number ln of A being the mass number, how this number varies. So you can see the correspondence here. So but down here you have protons, then you have a bit heavier helium, and then nitrogen and iron up here. So you can see that the composition varies from low at PeV energies to heavier at around 10⁻17 electron volts. And as you go to ultra high energies from here, you go to lighter composition and then something intermediate. But this is So this is the data in yellow, the yellow band here. But this is the data that we extract from one kind of estimator. And if you take another kind of estimator in green, then you get this other band. So the results are not extremely clear yet, although people in the community tend to believe this trend. So we have to be quite cautious still. And so what we can do with this composition is to try to fit the composition that various models of sources can give us in terms of cosmic rays, and then see if they are completely off this yellow band or not. But the thing is that actually, as soon as you have a source that can produce some level of heavy or intermediate elements, which is the case for many sources actually, you are capable usually of tuning the parameters of these sources in order to obtain a fit to this part of the spectrum of the composition trend. So for now, my personal take is that it's not that obvious to put constraints on models using the composition, but with more precise data, I hope that we will converge to something more constraining for models. But yeah, some models are already kind of not favored because of this intermediate composition. Now that we've looked at these observables one by one, we might also want to have a general look of all the possible sources that exist in the universe and see if we can remove some of them out of our candidate list. And for this, we're going to use what we call the Hillos diagram. So it's very simple. We say that in order to accelerate a particle to ultra-high energies, a source needs to confine it first. So the Lama radius of this particle has to be smaller than the co-moving size of the source. So this can be written, the Lama radius of the particle can be written like this, as a function of the particle energy and the magnetic field of the source. And then if you put this into this inequality, you can get an inequality on the energy where you fix the maximum energy to some number. And for example, you can draw then this diagram where you have the magnetic field strength of a source, its co-moving size. And if you are above this red line here, the source is going to be capable to confine and maybe accelerate particles above, protons above 10 to the 20 electron volts. Because of this Z charge here, which favors heavier elements, heavier nuclei to accelerate particles to higher, because of, well, heavier elements with higher charge can be accelerated to higher energies. You can put a bit lower limit for iron here. And if you put on this diagram many of the sources we know, you can see that, well, actually there are many sources down here that don't make it, but there are many sources that can, in principle, produce ultra-high energy cosmic rays. So, well, then we have to do one by one modeling of these sources to understand what's going on and if they're capable of really accelerating particles and having them escape from them. But you can see that there are two types of sources among them, steady sources and transient sources. Steady sources that will just emit cosmic rays over their long lifetime, and transient sources that are going to be a one-shot emitter and then stop. And these two types of sources will give different signatures in terms of ultra-high energy cosmic rays and multi-messengers. Another way of constraining sources in general, which is quite a similar way of reasoning, is to put is to use this inequality and say that if you want to to have a source accelerate particles, you need to have a acceleration time for the particle being shorter than the dynamical time of the outflow where it's accelerated. And so here are the parameters of the outflow, its size, magnetic field, and the Lorentz boost of the outflow. And then you can write the dynamical time of the outflow like this. And the acceleration time can be written as a function of the Lamer time of the particle times a factor that depends on the environment and the acceleration mechanism, and which is 1 at best, and usually more than 1, larger than 1. If you put everything together here, this and this, you can express the outflow magnetic luminosity, which is written here. It looks barbaric, but it's just the magnetic energy transformed into power. So, and this the magnetic luminosity is like a measure of the, is like a lower limit of the bolometric luminosity. So to some extent we constrain, and this magnetic luminosity has to be higher than 10 to the 45 ergs per second in order to accelerate particles to 10 to the 20 electron volts. So it means that this is a lower bound to the bolometric luminosity of a source if we want to produce ultra-high energy cosmic rays in them. So if you look at the population of sources that exist, you have some steady sources that could make it. And actually many transient sources that I didn't write down here that pass this cut. And because of the larger population of transient sources that pass this cut, my personal belief is that transient sources are more natural producers of ultra-high energy cosmic rays, but steady sources could also be as well. So if we look more precisely at these transient sources, we can also put some constraints on them and see which are the ones that are most likely to accelerate particles to higher energies. And then we have this kind of Hillas plot for transient. So a transient source, are those that have a short time scale, short-lived time scale. So this is the time variability shown here. And they have we can we can measure their bolometric luminosity or infer it. And on these plots, we show that naturally, as you go to higher luminosities here, you have higher proton maximum acceleration energy that are written in the contours here, in particular in red. So as you go to higher luminosities, you have higher proton acceleration energies. Oops, sorry, just because of this limit here. And then if you go to very high luminosity, then you have very strong magnetic fields and synchrotron losses kick in, which means that you can accelerate to less high energies, and then you have these diagonal bounds. So you can see that these triangles are the regions where cosmic rays can be accelerated to very high or ultra high energies. And there is a particular region here in the small triangles where cosmic rays can be accelerated to above 10 to 18 electron volts, where we typically define the ultra high energy cosmic rays. And there are many sources in here. So this is for relativistic outflows, for Lorentz factor of 1 for the outflow. And this is for mildly relativistic sources. And here you have many things like superluminous supernovae, black hole mergers. I didn't write it down here, but there are neutron star mergers as well. You have even supernovae and so on. And here you have blazar flares, low luminosity GRBs, tidal disruption events, black hole mergers, so on. So for transient sources, there is really a huge, many categories of populations that could be at the origin of ultra-high-energy cosmic rays in principle. And as I'm talking about transient sources, I would like to also talk about this very quite famous event that occurred 2 years ago, and that gives me further reason to believe that transient sources are probably a great bet for the origin of very high energy particles. And this is the this event I mentioned at the beginning, where we saw a neutrino from IceCube in coincidence with a blazar flare. So IceCube detected a very high energy neutrino at 290 TeV, and it sent an alert to many observatories, and these observatories saw that there was a surge in the luminosity of a blazar that was in the arrival direction of the neutrino. So it obviously made a lot of noise. And what was also very interesting is that then IceCube dug into its archival data and found from this same direction 13 plus or minus events above the background. So this also further gave weight to this discovery. So unfortunately, the level of detection of this coincident observation is not that high, of order 3 sigma, but and also there were, and it triggered a lot of discussions from a theoretical level. So what was observed was that there was, so this is the data here in multi-wavelengths. So there was an X-ray observations here. There were gamma ray observations and neutrino observations at this level here. And so many people did some phenomenological modeling of this source, the blazar flare, and found that if you model this source using a leptonic model, so saying that you have most of its photon emission produced by leptons that are accelerated and that radiate in photons, that cascade and so on, then you could fit nicely this part, but you would need to add on top of this some hadronic component to explain the neutrinos, because neutrinos can only be produced by hadrons. And the problem is that in order not to overshoot this photon emission by the hadronic component, you would need to have a neutrino flux level that is this low, and that is quite lower compared to what we observed. And if now you take a hadronic modeling, so you say that all the way the neutrinos and the photons are produced by hadronic components, then if you adjust the level of neutrinos to here, then you can see that dotted lines here for the photon emission that comes down here, up here actually. And you can see that because of the cascade of the gamma rays that are produced from the hadronic component, you have a lot of you should expect a lot of X-ray emission here. And this overshoots totally the X-ray observation that were made from this source. So theoretically, it's not very easy to reconcile all these observations. And maybe we were just lucky and we saw this, and this is the true model with a leptonic component and some neutrinos with a low hadronic component. And we were lucky, but then how do we explain that that there were other neutrinos found before? Then you have a higher flux. I mean, it doesn't really the 13 other neutrinos don't feel like we're super lucky this time, so it's complicated. And then people started to think about more complicated models with several zones of acceleration, interaction, and so on, which could fit. But yeah, so then it shows that if this event is true, which we hope, but this is not observationally verified, then it triggers a lot of discussions within the theory community, and it could really help us understand what's going on in the source. So, but this event was detected at PUCP energies, and so far all the neutrinos that we've detected and that with which we can probe these potential sources of ultra-high-energy cosmic rays are detected with IceCube below PUCP energies. And this is a problem because actually secondaries of cosmic rays, when they are produced via interactions, take up 5 to 10% of the parent cosmic ray energy. So for neutrinos, if you want to, if you have ultra-high energy cosmic rays above 10 to 18 electron volts, and you take 5% of its energy for the neutrino, you need to look at neutrinos that are above 10 to 16 electron volts. And this is not what we're seeing today. IceCube neutrinos do not directly probe ultra-high energy cosmic rays, although, of course, they help. So what we want to do is to go for ultra-high energy neutrinos, which would really help us understand, have a direct understanding of the, direct understanding of the sources of ultra-high energy cosmic rays. So this is where we want to go. This is what IceCube sees, and this is the ultra-high energy cosmic rays that we're aiming, that we would like to see in the next, with the future detectors. And the problem is that, so far, it's a big challenge because so far this region here for neutrinos is a no man's land, and we haven't detected anything yet here. And another thing that to me will be very important in the future, as shown by this TXS blazar flare, is that we will absolutely need to have connected observatories via various networks, such as the Amon network, which is capable of responding to the alerts of different observatories and be able to see if there are some transient events. So let me now talk about one way that we could use to hunt for these ultra-high energy neutrinos. And this is the ground experiment. The idea is the following. So if you have a tau neutrino that comes to the Earth, it's going to hit it could interact with the rock, the mountains, the crust of the Earth, and produce then a tau particle, which will interact with, which will decay, and the decay products will interact with the molecules of the atmosphere and produce an air shower. The reason why we need a tau particle is that tau neutrino is that if you have a electron neutrino, the secondary electron will just decay inside, will just be absorbed inside the mountain, and the muon, if it's a muon neutrino, the muon will just fly above the Earth and we will never be able to see it. Tau is perfect. It has a decay length that is quite good, short enough so that it produces this air shower, not too far. And then if you have an electromagnetic shower, so an air shower that is produced, you have an electromagnetic component inside this shower. And this electromagnetic component contains, say, electrons and positrons that are going to be deflected by the geomagnetic field. So electrons will go in one direction, positron in the other direction. It will create a current which will be moving, and this will produce a radio signal that we could observe around a few hundreds of megahertz. And what's very interesting is that this radio signal will produce a footprint on the ground of few kilometers. And this few kilometers is quite large. It means that you could plant some radio antennas at 1 kilometer distance and still be able to sample this signal quite well. And this means that you could have a sparse array, and sparse array means that you can go for very large array. And the idea of ground, we would use the radio detection technique, which is quite a very mature technique that has been experimented with various instruments listed here, and that have shown that we could very nicely reconstruct the primary particle parameter using the radio signal on the ground. And radio antennas are cheap and robust, and it's really ideal for giant arrays. So with ground, what we want to do is to cover to deploy 200,000 antennas over 200,000 kilometers square, not in one spot, but in 20 subarrays of 10,000 antennas in favorable sites in China and worldwide. So by favorable site, I mean, of course, a radio quiet site, but also with a good topography, because you saw that we need one mountain or slope on the side in order to have a target for neutrino interaction, and on the other we need a screen. So valleys would be quite ideal, and we also need easy access, and we also bump into administrative issues. So far we were quite happy because we did several measurement campaigns, a dozen of measurement campaigns, and most of them showed that the sites that we had chosen were excellent, but we had different issues, such as the site being quite flat here in Inner Mongolia, or the vegetation being very dense and access not being very easy here in Yunnan. But then we have some very good candidate sites in the region here at the verge of the Tibetan Plateau and the beginning of the Gobi Desert in China. And this is probably where we're going to deploy our first 300 antenna prototype. So within the ground collaboration, we have run end-to-end simulation chains in order to measure the performances of our plant detector. And the results are the following. So we see that the sensitivity of the full ground experiment should reach this level here. So we actually cut quite deep into this projected cosmogenic neutrino flux prediction. So these are the neutrinos that should be produced from the interaction of ultra-high energy cosmic rays when they propagate in the intergalactic medium with interaction on CMB and so on. And so if you observe with ground for 10 years, we can really reach this bottom of the gray region, which corresponds to standard parameters for ultra-high energy cosmic rays. And here we have a pessimistic region with pessimistic parameters for ultra-high energy cosmic rays, where I hope nature is not has not put the level of neutrinos. So this is the level of sensitivity that we're planning to have, and we are also going to have a very good angular resolution of 0.1 degree, and this is very good to do ultra high energy neutrino astronomy, because if we detect neutrinos at these ultra high energies, we of course would like to not just detect some neutrinos randomly, but to be able to point to the sources and be able to identify sources. And for this, we need very good angular resolution, and this will be achievable with ground. And finally, we would have also quite a good resolution on the composition, the nature of the particle. So at least we will be able to identify, to discriminate between nuclei and gamma rays and neutrinos, but also probably we could differentiate between the different nature of the nuclei if we observe when we observe ultra high energy cosmic rays. So do I have 5 more minutes? Okay, thanks. So in order to do this, we will have to overcome some technical challenges with ground. And one big challenge is the autonomous detection of radio signals. So far, all the experiments that have done radio detection have detected cosmic rays, and they have done so with a hybrid array where they had radio antennas and water tanks or scintillators that were able to measure the various air showers, the particles coming from air showers. So they first trigger with this water tanks or scintillators. They say that there is an air shower that has passed by, and they go look into the radio data and play with the radio data to reconstruct the primary particle parameters. But what we would like to do is to get rid of the secondary hybrid array and to just trigger on the radio antennas alone. And this is not easy because wherever you go, even in the most remote desert in China, you're always dominated by human noise in radio, and you have lots of transient noise, transient events that you register, and you typically need to have a rejection efficiency of 1 out of 10 to the 8. So you really need to have very good criteria. And so this is one big challenge that we would like to overcome, and this would mean a lot for the radio community in general. And we're going to test this on a dedicated test bench, which is our first prototype called Grand Proto 300 with 300 antennas. And other challenges will be to do reconstruction of primary particle parameters for very inclined air showers, when most of the experiments so far have worked on vertical cosmic ray air showers. And so we will use for this conventional methods and machine learning methods, which should be very efficient at doing this kind of rejection methods. So, and the other challenges that we will have at larger scale is to deploy and run 200,000 units over 200,000 kilometers square. So people ask us how we will do it, how much it will cost, who will pay for it. So the idea is to go for an industrial approach. So as soon as we have a prototype that is functioning, that the technical details are validated, so after we've tested everything, we want to just give our experiment to industry and ask them to develop, produce all the units and to deploy everything and to maintain it. This way, we would really have low failure rates and very nice efficiency, because when you think of it, for example, all the electric poles that are deployed massively, the phone antennas that are working very nicely everywhere, these are done by industry and they do it very well. So, and if we start talking about 200,000 units, industries pay attention. And also this will really cut the costs. So this is the direction we would like to go. But so yeah, sorry, I'm running out of time, but well, today we're working on the Grand Proto 300 prototype. We have an experimental setup that is almost ready with an antenna that has been tested and that is being produced. We have a layout geometry that is being finalized. We have the electronics also that is being, the electronics board that are being produced. And so the only thing we are slow at converging on is the site. On this we have been quite unlucky with the COVID situation. And also we have some discussions ongoing with the Chinese administration. But we are hopeful that in 2021 we can really deploy the antennas that we are currently producing. So today we have in Grand about 70 collaborators from 10 countries. So you can see here that they are many institutes from Europe that are working on the electronics, the simulation data analysis on the science case. We also have collaborators in Brazil, in the US, especially for some particle detectors for the Grand Proto 300 prototype. We have many collaborators in China for the antenna prototyping, also for unit production, and of course for the site management. And so, yeah, and we are preparing a memorandum of understanding between these institutes. And so if you are interested in this experiment, you can have a look at these references for more detail. And of course, if you have ideas and would like to join, you're most welcome. Join us and bring your ideas. Thank you.
Thank you very much, Kumiko. Lisa?
Yeah, thank you very much for the very interesting talk. If anyone has any questions, please they can make them now.
I have one question maybe to get things started. First, again, thank you very much, Kumiko. It was a really nice overview. My first question came up when you were talking about the flux of cosmic rays from transient events. I was wondering, we only see a diffuse flux of with the high energy cosmic rays. And out of that, can we tell if the main sources are transient or steady state?
Yeah, it's a good question because, well, one thing that should be clear, and I didn't mention it here, is that we will never see ultra energy cosmic rays in coincidence with other messengers, just because for transient events, because you have cosmic rays that arrive later than the other messengers because of their delay, their deflections in the magnetic fields, which induces a time delay, which can be of order 10,000 years for a 1 degree deflection over 100 megaparsecs. So yeah, but so from the diffuse cosmic ray that we see with Auger, there could be some ways of telling if the sources are transient. For example, if you look at, there could be specific signatures of transient sources in the anisotropy. So cosmic rays with cluster would be distributed a little bit differently according to whether they are transient, the sources are transient or not. This is like, sorry for the noise. But yeah, because actually typically the regions where you have sources would be a bit more peaked because of this kind of time delay effect. It's a rather fine thing that you would have, it's difficult to explain like this, but yeah, when you do the calculation, it actually shows that you could have more striking features there. Other ways, maybe you could also, in the spectrum, you could see some, if there is a transient source, maybe you could have some, yeah, I'm not sure. Yeah, I saw a paper by Baxman on this, that they could, if there are some rare transient sources that are dominant in the spectrum, there could be some features above GZK. Yeah.
If they're close.
If they're close, yeah, of course, yeah. These are the things I can think of.
Yeah.
Yeah, but then you would have to really rely on the secondaries, I think.
Yeah, no, I agree.
Yeah.
Thanks. Actually,
I don't see the questions, so yeah, because because I'm sharing my screen and I.
No, it's okay. I think there's no written question, so Alicia, just go ahead.
Yeah, if anyone has any questions, any additional questions, they can make them now, either raise their hand or write them. In the meantime, I wanted to ask, you mentioned that you were thinking about using some machine learning techniques for grant. Have there been any developments in that aspect, or maybe how exactly those techniques would work?
So I'm really not an expert on machine learning, so well, take my answers with a pinch of salt. But yes, indeed, inside Grant, there is a group working already on developing these methods. It looks quite promising. So there are two main projects. One is about this autonomous triggering, and the other is about reconstruction. So about looking at a footprint pattern and be able to tell from the footprint, thanks to machine learning, what's the primary particle parameters. For autonomous trigger, the idea is to have to feed the algorithm with many simulations of different air shower simulations and the signal in radio. So say, for example, the footprint or other observables, even the traces, things like this. And yeah, actually also on the traces to work at the antenna level, and that the algorithm be able to recognize whether it's a signal that would be a particle shower or some background noise. So that's roughly the idea. And what has been shown is that actually it's not just in Gran, but also some Auger people have in AERA have worked on this, and they seem to, it seems like the efficiency of these methods are pretty good, and that you can really extract from a lot of noise, like some signals that are at 2 sigma level, something like this. So it looks quite promising.
Okay, thank you very much. So I don't think we have any more questions, and we're actually.
I have one final question, if you don't mind.
Sure.
When you showed your slide 12, that's your slide where you were showing the anisotropy.
Yeah.
Yeah, due to protons and to heavier nuclei. So I was looking at your right hand side upper plot, and yeah, that one. So how dependent is that on the galactic magnetic field? Because this should come with a fairly large uncertainty, right?
Yeah, definitely. I think this one. So this is the Calvez et al. Plot, but I think the others, especially the Giacinti paper, tried many magnetic field parameters. So, and I think it was quite clear that even if that you could put some limits, even with increasing the field, or but because you have bounds on the magnetic fields as well anyway. So yeah, you have some constraints, and if you go to the limits, you can still, but okay. There is of course a dependency.
Okay, I see. All right, thanks.
Okay, so we thank Dr. Kotera for the very interesting talk once again. I would like to also thank the audience for attending the talk, and we would like to invite you to next week's colloquium. It will be given by Edith Sayer, and it will be actually about COVID-19, titled COVID-19 en el Perú, lo que los datos no nos cuentan. Thank you all very much.
Thank you so much, Kumiko. Thank you, everybody.
Thank you. Thanks a lot.
Talk to you soon.
Yeah.
Bye-bye.
Bye-bye. Take care.